In this video, we'll discuss how the Laplace transform is a linear transformation. What do I mean specifically by that? Well, that's the same two properties that we saw for linear differential operators. The Laplace transform applied to a sum of two functions, so if I take f of t plus g of t and I take their Laplace transform, I can just compute them individually. So I can calculate Laplace of f of t, Laplace of g of t, and add the results together. This property is true because the Laplace transform is ultimately some kind of integral, and integrals have this linear property as well. The other property of being linear is that if I have a constant multiple, so c times my function of f of t, then I can just pull the constant out and calculate the Laplace transform of f of t. Here c must be a constant, don't apply it to anything involving t. All right, let's do an illustration of that. We could take the Laplace transform of 4 minus 5 times e to the minus 2t. There are two terms in this. One is a constant term, and the other one is an exponential term. And in the previous video, we saw what the Laplace transform of 1 and of an exponential should be. So first we're going to apply the linearity here and do it term by term. I'll have the Laplace transform of 4. And then I'm adding to that the Laplace transform of minus 5 e to the minus 2t. Bring out any coefficients, like the 4 can come out and be 4 times 1. I know the Laplace transform of 1. Bring out the minus 5. It's minus 5 times the Laplace of the exponential. We now take advantage of our previous calculations and avoid doing any integrals whatsoever. This is 4 times 1 over s. And then the Laplace of the exponential will be minus 5, and it's 1 over s minus the parameter a. In this case, that parameter is that coefficient minus 2. So it's going to be s minus negative 2. So 4 over s minus 5 over s plus 2. And you may, this is up to you, but you may simplify this further and get a common denominator. So you could multiply the top and bottom here by s plus 2. And multiply the top and bottom here by s. If you do that, you'll have 4 times s plus 2 minus 5 times s, and that would all be over that common denominator of s times s plus 2. Simplifying the numerator, 4s minus 5s gives you minus s, and then 4 times 2 gives you 8. So just simplifying and combining like terms, we get this expression here for the Laplace transform of this linear combination of a constant and an exponential function. This is fairly typical. The Laplace transform of nice functions turns into some sort of rational function, a rational expression in this new variable s. So we transform a function of time into some sort of rational expression involving s. It's fairly complicated looking at the end here, but at least in the denominator you can take note that that factor of s came from the 1 over s, which came from the constant term 4. And the factor of s plus 2 in the denominator came from the s plus 2 in this term, which came from the exponential e to the minus 2t. So you have some anticipation that back in the time or t domain, where my original function was, s corresponds to that constant, and s plus 2 corresponds to that exponential.